Welcome back. This is Dr. James Joey, Huntington College, Quantitative Methods. We are in Chapter 9 of your book, even though it says 11. And we are on Section 9.4. So if I can get this done here, there's 3, 9.4. Here we go. Okay, now here we're assessing the utility of the model, making inferences about the slope coefficient B1. So now that we've specified the probability distribution of our error term, epsilon, and found an estimate of the variance, s squared, we are ready to make statistical inferences about the linear model's usefulness in predicting the response y. This is step 4 in our regression model procedure from chapter 1. Oops, click there. Okay, now suppose that the reaction times of the drugs are completely unrelated to the percentage time. So the percentage of the drug has no effect on the reaction times. Okay, if that were the case, then the values of beta naught and beta 1 in our hypothesized probabilistic model, that means that there's no change in y that is a part or is in the deterministic part of the model. Y is just random as far as x goes. Okay, so the amount of the percentage of the drug we give them has no effect on reaction times. It would look something like this. Here's beta naught, and these little reaction times based on how much of the drug we give to people, y, are just randomly distributed. The value of x has no real effect on y. Okay, so that would mean that beta 1 is essentially 0. It has no effect. Okay, so we would first off like to test a hypothesis, and I don't have the slide for it here, but we want to test the hypothesis. Okay, and I'm going to use my camera here to show it to you. Okay, we would test this hypothesis. Our null hypothesis is always that beta 1 is equal to 0. Okay, that it has no effect on the reaction times for these drugs. Our alternative, H sub A, is that beta 1 is not 0. Okay, so we're going to test right here to see if that beta 1, that slope coefficient, has any effect at all on, in this case, reaction time. So I'm going to put my camera back there. Okay, so that's what we're testing. Now, in order to do this, we need a sampling distribution for beta 1. Now, the 4 assumptions about the error term from section 9.3, the one we just did, the sampling distribution of the least squares estimator B1 hat of beta 1 hat of the slope will be normal with a mean beta 1, the true slope, and this standard deviation here. So the standard deviation of beta 1 hat, the estimator of the slope coefficient, is equal to sigma, which is the standard error, divided by the square root of SSXX. Go to 1110 here and look at this model. So here's beta 1. It is distributed normally with a standard deviation of sigma. Now we don't know sigma, so we have to estimate it by estimating S. Okay, and we did that in a previous chapter and refer to this as the estimated standard error of the least squares slope coefficient beta 1. So it's equal to the standard error divided by the square root of the SSXX. Okay, that's what it looks like. Okay, so when we do this, we have our null hypothesis, beta 1 is equal to 0. Okay, And our alternative might be that beta 1 is less than 0. Here we might be saying, well, we think that beta 1 could be negative. And that would be a one-tailed test. Okay? A two-tailed test, beta 1 is equal to 0. Our alternative is beta 1 is not equal to 0. And the test statistic here is a t. Okay, we always use the t. So t, the test statistic, is equal to beta 1 estimate, the estimate of beta 1 hat, the estimate of our slope coefficient divided by, going back here, the standard error of our regression divided by SSXX. Okay. Here, depending upon which type of test we're doing, our rejection region will either be t less than negative t alpha. Here we're doing a less than one-tailed test. If that was a greater than sign, this would be t greater than positive t alpha. If we're doing the two-tailed test, the rejection region is the absolute value of t is greater than t alpha over 2, because remember, this is a two-tailed test. So we got to divide alpha by 2. Okay? Where T alpha and T alpha 2 are based on n minus 2 degrees of freedom. Previously, we had 1 degree of freedom. Now we have 2 here. Okay? And that is because we calculate 2 means. One for the beta naught, the constant, and one for the x variable in our model. So remember, n minus 2 degrees of freedom. If we had more than one x variable, say in a multiple variable linear regression model, this would be the constant plus all of the different x variables or predictor variables. Okay. Now, the conditions required for a valid test are the same as for simple linear regression, the 4 assumptions listed in 11.3. So we would go and look up this rejection region in the back of the book. Okay, we have an alpha of 0.5. So we would go to your T tables in the back of the book. All right, and that is on page 556, and I'm going to show it to you in a minute. We had 5 observations, and we're doing a two-tailed test here. So our T is alpha over 2, which is 0.5. That was our alpha over 2, so it's 0.025. So we're going to go down this row, okay? And we had 5 observations, but it's n minus 2, so we have 3 degrees of freedom. We look right here. Oops, I'm sorry. And that would be 3.182. They've got a different number on the slides here, 3.182. Oh, no, there it is. There's our area of rejection here. Okay, 3.182. Any value for our t that this is a two-tailed test, that goes in between negative 3.182 and positive 3.182, we are going to fail to reject the null that beta 1 is equal to 0. It has no effect on reaction times. If we get a t value that falls outside of this area of rejection, say out here in the yellow or out here in the yellow, then we're going to reject the null hypothesis, and the evidence supports that x has an effect on the value of y. So when we calculate this t, this is our calculated t, we got 3.17, okay? And that came off of our printout. Our t is 3.66, we're calling it 3.7, and that falls outside of the outside in the rejection region. So here we would reject the null hypothesis that x has no effect on y, that the percentage of the drug has no effect on the, sorry, I'm trying to show you where we got that number. at 0.025? Let's see. There we go. And then we went down 3 degrees of freedom. You can see here. 3.182 is where we got the critical value. And our calculated value turned out to be 3.7. We got that off the printout. Okay. So that says we failed to reject it. That the percentage of the drug X does have an effect on Y. Okay. We also have a p-value. That p-value is the probability of getting a calculated t of 3.7. It's the probability of everything of getting a 3.7 or greater. So from here all the way out, the probability of getting a t that big if beta 1 was 0 is 0.035. Okay? And that falls outside of alpha over 2.025, so we reject the null. Okay. Interpreting p-values for beta coefficients in our regression. Doing an upper tail test, HA beta 1 greater than alpha, a p-value is equal to p over 2 if t is greater than 0. It's equal to 1 minus p over 2 if t is less than 0. So if we have a negatively calculated t, 1 minus the p over 2 is the probability of getting a t value that's small when the value of beta 1 is 0. Okay. We're doing a lower tail test that gets, it's the same. P over 2 if t is less than 0. I'm sorry, it's flipped upside down, my fault. P over 2 if t is less than 0. 1 minus p over 2 if t is greater than 0. Okay? Where p is the p-value reported on the printout, and t is the value of the test statistic. Okay? We can also set up a confidence interval for the simple linear regression slope beta 1. You take the estimated value of beta 1, so here we would have gotten that from our printout of 0.7, okay, plus or minus t alpha over 2. We looked that up here, sorry, and that was 3.182. And then we would multiply that by the standard error of beta 1, where the estimated standard error beta 1 is calculated with the following formula. And again, that t alpha over 2 is based on n minus 2 degrees of freedom. 5 observations minus 2 would give us 3 degrees of freedom. Conditions required for a valid confidence interval. Again, the same 4 assumptions that we listed in section 11.3. Okay. Printouts will oftentimes give you this. So here, if we calculated that confidence interval, we would take the standard error of beta 1, calculated here, times our 3.182, critical t, when we looked up in the book. Okay, we would have calculated this. We would have had to go and calculate SSXX, that's x minus x bar squared. Okay, take the square root of that, divide the standard error by that, and that would give us the standard error for beta 1. Okay, and then we could get an upper and a lower bound. So the upper and lower bound for that time x, okay, it was percentage of x, but okay, came out to be 0.091 to 1.309. 0.7 is right in the middle of that. Here we have one for the Gaussing question, right, from Minitab. There's your coefficient. The guess is 0.3079. The standard error of the coefficient is 0.1900. We got a t of 1.62 and a probability here of 0.118. Okay, so depending upon what our alpha was, we could determine whether or not guess has a positive effect on pipe, whether guess does influence the value of pipe. Okay. Thank you very much. Have a great day.